you made it! Last section of chapter 7. Applications of exponential functions. Okay, we're going to try to understand this using some examples. So, let us pretend for a moment that you, say, won $10,000. And you decide to put it in the bank, and then you're going to use it as a vacation fund. And you decide that every summer you're going to take out 7.5% of your money. And so you might be thinking, well, how long is that going to last me? How many nice vacations am I going to go on? So you might just say to yourself, well, how much will there be after 10 years? How much left after 10 years? Now, this hopefully is sort of reminding you of problems we did back in chapter 6. Hopefully it's not a nightmare for you. So there's different ways to think of this. I like to kind of refer to it as a middle school technique. The middle school technique might say, well, okay, if I'm going to take 7.5% out, I need to figure out what 7.5% of 10,000 is. Maybe I'll do a proportion. Who knows what I'd do, but I'd figure that out and then I'd subtract it from 10,000. So then I have less money in my account and I'd have to do it again. I'd have to say, well, what's 7.5% of the amount of money I have now? And you would go through the similar process. So what I tried to talk to you into in chapter 6 was realizing there is actually an easier way to do it, where if we think about the fact that we're taking 7.5% out, rather than thinking about how much we're taking out, we could think about how much is left. So if we take 100 and we subtract 7.5, we get 92.5. So rather than a two-step process where I have to say, well, what's 7.5% of 10,000, and then I have to subtract it, I can instead take my 10,000 and multiply it by 0.925. I have to change my percent to a decimal and come up with how much money I have after my first year. And that, I believe, turns into 9250. Then I can take that 9250, so this would be my second summer, and multiply that again by 0.925 because I'm going to take another 7.5% out, and I'll get another number. I believe it's 8556.25. And I could keep doing that till I get to the end of after my 10th time I take money out after 10 years. Now, in the last chapter, and if you struggled with it, maybe this is the moment where you can understand it. What we did was we had this little equation, and this was one that we had to understand, where we said a sub n is just equal to whatever we start with, and this would be geometric because we're continuously multiplying, times the common ratio to the n minus 1 power. Now, the tricky part here is that if we think about the 10,000 as year 1 in the sort of the first position, after we go 10 times taking the money out, we're actually ending up in our 11th position. And so we would take this 10,000 and we would multiply it, apologize, I'm a little smushed on the board here, times 0.925 to the 11 minus 1, that would be the 10th power. Now, since we're now talking functions, I would suggest that maybe we could put this in our calculator. So I'm going to go ahead, I'm going to hit my y equals here, and I'm going to type in 10,000, and I'm going to multiply that by 0.925, and I'm going to put an x up above. So I'm going to raise that to the x, because this chapter is all about exponential functions, and so that's what this thing really is. So the cool thing about putting this into my calculator is that then I can go to my table and I can actually look at the numbers. Let me just get this down. I don't care about the negatives in this case. So you can see, as we said, at 0 we were at 10,000, and then after a year we're down to 9,250. Now the one problem is we have sort of a rounding issue because of the space here. So we might actually want to do the real calc out, but this will get the point across. So when I come down here to how much money I have after 10 years, then, or when I raise it to the 10th power. So remember, this is because my exponent is a 10, then this would be my answer to how much money I actually have after I've made 10 withdrawals. So if you were to multiply this out on your calc just to be a little bit more round it into dollars and cents, you would find it to be $4,585.82. Okay, so just to review what I just did here, what I basically did was I said, well, wait a minute, let's actually kind of create a function here, and in place of having this putting a 10 in, which I could do on my main screen, I turned it into x and put it into my y equals so I could use my table. So I just want to introduce some new notation to you, which is often used when we do these types of problems. And instead of, this is kind of the chapter 6 way we wrote this, where we said a sub n is equal to a sub 1 times r to the n minus 1. In chapter 7, we're going to start sort of looking at the notation that's used in financial world, where we say a is equal to a sub naught, is how we say it, times 1 plus r to the t. So basically, a stands for the amount. This a sub naught stands for the initial amount. This r stands for the rate, and t stands for time. So in some ways, this equation helps you a little more because it forces you to do this subtraction. Now, the one thing about the rate, when you put it into the equation, it has to be put in as a decimal. So for this particular situation, if we want to know what is the amount, then the a naught, the initial amount, was that 10,000. And then what we would do here is we'd say, okay, 1, and then because we're taking money out, we're going to actually subtract. And so this right here is going to actually do that subtraction that I had to think about on my own. So I'm subtracting, I'm taking out 7.5%. Notice I put this into decimal form. And then the amount of time I'm going to do it is for 10 years, which gets to the same answer that I had on the other board. So this is sort of a new notation used very much kind of in financial worlds that helps us figure out, and it's the reason this is in this section is because oftentimes what we do is we leave this as a variable so we can figure out this is how much after 1 year, after 2 years, after 3 years, etc. Okay, so now what this is called it's compounding money. And once you start putting money in a bank, you might start understanding this, so maybe you've met this before. But I want to go ahead, I'm just going to rewrite this original equation again. A equals a naught times 1 plus r to the t. So basically this equation right here figures out how much money you have when we do what we call compounding annually. And so what compound annually means is that the bank, once a year, so in this case I'm trying to get you to think about this from the perspective of making interest on your money. So this is a situation where once a year the bank sees how much money you have and whatever the interest rate is, maybe it's 5% interest or whatever, they take 5% of the amount of money you have in your savings account, figure out what that total is, and they throw it back in. And then a whole another year goes by, whatever happens in your account happens, and then they do the same thing. So we do it once a year based on however much money you have in your account at that point in time. So, just to think about this, I think I've kind of gave you a similar example before. If I have $100 and it's going to be compounded annually at 5%, and the question is, how much do I have after 1 year? So, when it's annual compounding, I'm going to just use this little equation here, and I'm going to say, well, A is equal to 100. Once again, I'm going to let this equation kind of do the work for me, times 1 plus, this rate here is going to need to write it as a decimal, 1 plus 0.05 to the first power. Now if we multiply that out, turns out it's $105. So then this whole thing about compounding annually is fine, but what if they could compound it more often? So like say they could compound it monthly. So that would mean that the bank's actually going to go in, see how much you have every month, take a percent of it, whatever it may be, throw it back in, and then the next month comes by. So you get compounded more frequently. And so in this case then, say it was compounded monthly, the way it would be calculated is we take 100, we multiply that times 1. But now we need to take this percent, because this is an annual percent of 5, and we're going to divide it by 12, because we're going to do this compounding every month. And so my time now has to be raised to the 12th power, because it's going to happen 12 times. So the one thing you do need to be careful about is that our annual interest rate has to be divided by the number of times it's going to be compounded. And so what ends up happening then, instead of having $105 at the end of the year, you end up with $105.12. So hopefully this makes a little sense, because it seems like your money's making more money for you. So then you might say, well, let's just go for it. Let's do daily compounding. Okay, so daily compounding, then we start with that 100. But now, instead of compounding monthly or annually, I'm going to divide this by 365 and raise it to the 365th power. And it's very minimal, but at the end of the year you would have $105.13. Now if we started with more than 100, then that difference would be bigger. So to allow for this, and these are numbers, these are equations that are not given on the cheat sheet, and usually if you needed them you would be given them. I would say that if you can understand this, you might be able to work your way into it. So I'm going to write just a little more complex version of that, and that would be whatever our initial amount of money is times 1 plus r over n, and then all times raised to the nt. And so what the r is still the rate, and this is the number of times compounded annually. And then this t is the number of years. So that if it was 2 years and you were compounding monthly, you would have to, this number would end up being 24. Now don't worry if this seems kind of confusing right now. At this point, if you can just sort of accept these equations, and we'll do some practice that'll help you understand. Now I do need to introduce one other thing, and that is this concept called compounding continuously. And so without getting too messy in deriving this, compounding continuously would be, you say, well, let's go annually. No, let's go monthly. No, let's go daily. No, let's go every hour. Let's go every minute. Continuously is this concept of continuously compounding. And mathematically, as it turns out, we can figure out an amount. And if you start listening to commercials about banks or just look in the newspaper, you'll see this compounding continuously. As it turns out, if you want to figure out how much money you have when it's compounded continuously, we get a different equation that has this famous variable called E in it. And once again, this R is still rate, this T is time. And E, I'm going to show you on your calculator where you can find it. We should have already done this in class, and this is our initial amount of money. Now E is an interesting number. There's all kinds of stuff on the internet. This is a site called Math is Fun, and it shows you what the number E is. It is irrational. I kind of think of it as kind of a cousin of pi. It has similar behavior since it's irrational. It does have something to do with logarithms, which are coming into the next chapter. Its reason for being, and we should have talked about this in class by the time you see this video, comes from some different sort of limits, okay? And once again, if you want, this is in the Math is Fun website, which you could check out if you wanted to. There's also another place we find E, and that is if we take a sum where we take 1 plus 1 over 1 factorial plus 1 over 2 factorial, etc. It is not your business to have to know where E came from. I just want to let you know, give you a little background if you're curious. Okay, so what is this all about? Basically, we're going to practice some different problems where we're going to have to figure out how much money we have after a certain amount of time based on compounding. So I just want to do a couple more examples and then just let it go for this section. So here is a situation. You may be given information. There's a state park, and it is told that the deer population, or it's supposedly, is approximately 2,000. And they're increasing in population so quickly that it's considered to be continuously. So increasing continuously. Whoops. Increasing continuously. And so then the problem may ask you to continuously at a rate, we need some sort of a rate, at a rate of 4%. And the question will then say, well, how many deer will there be in 10 years? So how many deer in 10 years? So the thing that you're going to need to do is train yourself to sort of be on the lookout for this continuous increasing. So when I see that word continuous, this equation then is going to come into play, where I use this famous E. So A then is going to be equal to A naught times E to the RT. So in this particular case, there's 2,000 deer to begin with. I'm going to multiply that times E to the, I need to take that percent and put it into decimal form, and T in this case is 10. So just to show you how to do this on your calculator, if you, and I should have hopefully shown you this in class by the time you're listening to this, if I type in 2,000, now I have two options where to get this E. One of the options is to hit second divided by, and the E will come on my screen, and then I can just raise that. Now I got to be careful if my calculator doesn't give me the exponent to put it in parentheses. Raise it to the 0.04 times 10. And you get an answer. There would be 2,900, we'll round it to 2,984 deer. Another thing you can do is go 2,000 times, and if you hit second ln, it's going to give you the E already with an exponent in an exponent form. And you would put the same 0.04 times 10. Okay, so I'll just come back here, and the answer ultimately is 2,984 deer. Okay, one more question. I don't want to run too long on this video if I can help it. Another place we see this continuous compounding, or also decay, is in chemical elements decaying. So this would be an example of a problem like that. So the decay constant of radium is negative 0.0004 per year. Notice it's negative because it is decaying. How many grams will remain of a 50-gram sample after 20 years? Okay, so this, notice there's no words about continuous, but you need to realize this whole concept of decaying. It's an element like radium or whatever, it doesn't just decay once a year, it continuously decays. It's just like anything. It's like a banana that you sit on the counter that starts going bad. It doesn't happen all of a sudden, it happens continuously. So once again, even though it doesn't say it directly, this is a situation where we want to use this equation. So our original amount was 50 times E, in this case the rate, and we do need to put it in as a negative because it's decaying, times T, which in this case they've told us they want us to figure out how much of the stuff is left after 20 years. So if you use your calculator to multiply that out, you would end up, if you were to round it to tenths, at 49.6 grams. Okay, I'm going to leave that at here. Please go into mathexcelforschools.com, give the quiz a go, and we will chat a little further in class about these concepts.